Okay, so I just recorded a video and it didn't work. The file was corrupted, so I'm starting over, which is why my notes already have writing over on them. But Chapter 9 is going to continue with Chapter 8. So we're going to be looking at electrons outside the nucleus. And then this will take us into Chapter 10, which is going to be bonding, Lewis structures. But I think Chapter 9 should be a pretty good review from Intro Chem. So what we look at first is how the electrons are organized outside of the nucleus. And the first way they do that is by the energy level, or the energy shell. I use both terms and kind of don't remember which one. To me, they're the same. And that is that principal quantum number we learned in Chapter 8. So if we look at like kind of a generic atomic structure, right? We have our nucleus in the center where our positive charge is. The electrons want to be close to that positive charge, but they don't want to be close to each other, right? Because they repel each other. So we have a first shell or energy level, second, third, fourth, and that's the first way that those electrons get organized. The first shell, best place to be, but it's very small. We can't fit very much. Once that's full, we then go to fill the second shell, then the third, then the fourth. And however many shells or energy levels are filled depends on what row on the periodic table. So for example, like magnesium is in row 3, so it has 3 occupied shells. But something like strontium is in the 5th row, so it has 5 occupied shells. So obviously the bigger the atom with more electrons, the more shells that will be occupied. Now within the energy shell or the energy level, you can have the sublevel or the subshell. And those are your SPDF blocks on the periodic table. So when we look at our periodic table, we've got our S subshell or sublevel, right? The alkaline earth metals. Now I think for the purposes of electron configurations, helium needs to be right over above beryllium. So this is your S block. Your transition metals, right? This is your D block, all right? And then when we get over to the 6 tall columns on the right, this is your P block, P sublevel, P subshell. And then down at the bottom, you have your F subshell, right? These are your lanthanide and actinide series. And what these are is these are different regions in space. So like if I have an S subshell, it's a spherical. I always remembered S for sphere. And those electrons are orbiting around the nucleus. And that mimics the shape of the nucleus. So energetically, S is the best. With P, you have places that are along the axes where you can put electrons. So moving side to side, moving up and down, moving out and back. And then D comes along and says, well, okay, well, instead of being on the axes, let's go between the axes. So they have names like DXY, DYZ, DXZ, right? And so these are just different like spaces for those electrons to, again, be as close to the nucleus as possible, but to stay away from each other. That's kind of the goal with this. All right, and then within that subshell or sublevel, there are specific orbitals. So when we were looking at the P subshell, right, that is all of those 3 directions, right, the X, the Y, the Z axis. But the orbital is just on one dimension. So when I look at the P subshell, it includes all of those 3 different spaces, the X, Y, and Z. But an orbital is just one of those. So the P subshell has 3 different orbitals. The rule is that one orbital can only fit 2 electrons. So if I have a P orbital, I can fit 2 electrons. But if I have the P subshell, all 3 orbitals together, 2, 4, 6 electrons total. And I can remember that because there are 6 columns on the periodic table. When I look at S, there's only 2 columns, which means I can only fit 2 electrons. And if it's 2 electrons per orbital, that means there's only 1 orbital. And that's it. That's that spherical orbit. That's it. When I get to D, if I count over from scandium to zinc, I have room for 10 electrons. So that must mean that there are 5 different D orbitals. And then down at the bottom with my lanthanide series, if I count over, there's 14 electrons total. So that must mean that there are 7 different F orbitals. All right, so when you go to fill the atom, the electron structure, you just go in order of the periodic table and you follow it along. You just have to remember there's a couple of glitches. So we do 1s fills at 2. There's nothing over here in 1p, right? So then we'd go 2s fills at 2. Then we'd have our 2p fills at 6. 3s fills at 2. 3p fills at 6, and then 4s2, and then when we get to D, we want to remember to take row minus 1. So even though this is row 4, this is a 3D space. And the reason for that is it all comes down to energy. Energy is almost always the answer with a lot of things in chemistry, like what's energetically best? And so what happens is even though the 4s is farther away from the nucleus than the 3D is obviously in an inner shell, the third shell. The spherical orbit is just so much energetically better than the D orbitals that the electron actually says, you know what, I'd rather just go up to the fourth shell and have a spherical orbit than go down to that third shell and have to be in those strange orbital spaces. So there's a little bit of a glitch here. Now you also have to remember that the D orbitals and the orbitals in general, like as they fill, their energy sort of flexes a little bit. So what you'll see is that the 4s and the 3D are pretty close in energy. When they start empty, the 3D is higher in energy. So the electron doesn't go there, it goes to the 4s first. But as those D orbitals fill, they actually lower in energy, and they actually become, once they're full, they become core electrons. So kind of interesting. That was part of the reason why I did my master's in inorganic chem, because I kind of thought the transition metals were pretty interesting. Anyway, so, oh, sorry, back to order of filling. So 4s fills at 2, 3d fills at 10, gallium goes back to what I call normal counting, 4, right? 4p fills at 6, 5s fills at 2, 4d fills at 10, again, that glitch, row 5, but it's a 4d. Indium goes back to normal, 5p6. Then we go 6s2, and then we get this gap in atomic number, and those elements there are your lanthanide series. And you want to remember for F, take row minus 2. So even though this is row 6, this is 6s fills at 2. Then we come down here and do our 4f that fills at 14. Then we go back and do our 5d that fills at 10. Right? And then back to normal. Thallium would be 6p, that'll fill at 6. Then 7s2, 5f, right? Because row 7, this is the 5f fills at 14, and then 6d10. So just remember, you put your principal quantum numbers right here, your rows on the periodic table, and then remember that for D, right, it's row minus 1. So even though this is 4s, this is your 3d, where now you're actually looking at a principal quantum number of 3. Going back to what we learned in the last chapter, if we're looking at a D subshell, that means the L is 2, right? Remember that. So we're kind of tying in what we learned in the last chapter. As we do the order of filling, right, we just talked about that. I think it's easier to go with the periodic table. When we look at orbital diagrams, we're going to remember that only 2 electrons can occupy any one orbital space. That's the max. So like we were talking about with P, I can only fit 2 electrons on the X, 2 on the Y, and 2 on the Z. Altogether for the subshell, we can have 6, but any one orbital can only have 2. That's always the rule. All right, and then on the next page, what we look at here, when we do those electron configurations, electrons will always occupy the lowest energy orbital first, the 1s, right, that always goes first. No more than 2 electrons can fit in an orbital, we just talked about that. The 2 electrons in the same orbital must have opposite spins. We saw that with that spin quantum number in the last chapter. It's either plus or negative 1/2, right, for that m sub s. So we're going to show opposite spins when we do orbital diagrams. Electrons would rather sit separately if they could. They lose energy by having to pair. They don't like having to pair because they repel each other. But it depends what the options are. Are they going to have to jump up to a higher energy level to sit separately? That probably energetically is not going to be a benefit. So what we're going to look at are the degenerate orbitals. So that's coming. All right, and then what we need to also focus on are valence versus core electrons. So valence are the electrons that decide the bonding. These are the electrons in the outermost occupied shell, all right, which again is your N, your principal quantum number. Okay, any unfilled D or F. electrons, right? And we probably won't be looking at elements in the lanthanide or actinide series, so we're just going to focus on the transition elements. That if this is something we'll add from that we didn't do in intro chem, that if we have unfilled D subshell electrons, those electrons also act as valence electrons. Even like, for example, like if we look at titanium, we're looking at a 4s2 and a 3d2. Even though the 3d is not the highest n, the 4s is 4, right? Because the D subshell's not full, those D electrons also act as valence electrons, right? And so that's why we see titanium as either a +2 or a +4 charge. All right, so that's going to come up. I think this is a good place for me to stop the first video just to make absolutely sure that my video is recording this time. All right, so I'm going to pause there.